Today we are going to discuss about the SIP technology installation process. So let's begin with the heartbeat of SIP, the strategic injection pulses of oxygen. Imagine the blast furnace as a living creature and oxygen as its breath, but this breath isn't continuous, it's pulsed. Each sphere receives a sharp burst of oxygen at 20 bar pressure, lasting just half a second per cycle. That's like a heartbeat fast, rhythmic, and powerful. Why pulse? Because it energizes the raceway without overwhelming it. These high-speed valves act like the furnace's lungs, delivering oxygen with a surgical timing. And while the pulse is dramatic, there is also a gentle stream, basic load oxygen that flows continuously to cool the lungs. It's like a whisper alongside the roar. Safety is woven into every fiber of SIP. Venting system ensure no pressure buildup unexpectedly. Uh, the nitrogen breakup stands like a firefighter ready to cool purge or protect if oxygen falters. This is not just engineering, it's a choreography, a dance of pressure, timing, and trust. And huge synchronization is required. Now let's explore the hardware, the bone of a muscle of SIP, that is uh, that is the high pressure oxygen ring main. This is the artery carrying life giving oxygen at 20 bar. It's supported by a buffer tanks, pressure control station, and a network of shutter valves, manual and automated. Strategically placed around the blast furnace, each tier gets its own SIP box. Uh, think of it as a control cockpit. Inside, a fast-acting solenoid or pneumatic valve capable of opening and closing in under 100 milliseconds. That's the faster than a blink. A flow meter monitor oxygen delivery, a cooling valve ensure a steady low flow, and if oxygen fails, an emergency nitrogen train kicks in. Valves, interlocks, and safety vent piping all spring into action. Local control logic rely on PLC, sits the field mounted, ready to respond, and then there is a lance itself, slim, robust, built to survive, made of stainless steel or Inconel. It's designed to withstand high temperature and corrosion. It's not just a pipe, it's a precision instrument. Now, safety is not a just checkbox in this implementation of SIP. It's when working with the high pressure oxygen, every detail matters. A full risk assessment is non-negotiable. Every seal, gasket, pipe, and vent valves must be rated for the oxygen service. So there is no room for compromise. Installation must be strategic. We do not overhaul the entire furnace at once. Instead, we install SIP system during scheduled tier outages in small batches. These allow for a stepwise commissioning and minimizing the risk and maximizing control. Before connecting to the main oxygen network, every line must be pressure tested and leak tested. Imagine preparing surgical room. Everything must be precise and verified. That's the level of discipline SIP demands. Because when you are pulsing the oxygen into furnace at 20 bar, trust is built on preparation. Now, commissioning SIP is like a tuning a musical instrument. First, we test valve actuation, dry run using air or nitrogen before introducing oxygen. These ensure the system respond correctly without risk. We commission tuyers in batches, carefully monitoring furnace thermal load and process stability. It is not just about turning valves, it's about listening to the furnace. It's a raceway responding. Is the body stable? Pulse frequency and cooling flow are adjusted based on the live process data. It's a feedback loop. Observe, adjust, stabilize, and all these activity in a synchronized manner. SIP is not just a fixed recipe, it's a dynamic rhythm uh, tuned to the furnace need. As we have already shown in the previous slide regarding documentation and training, that is technology without training is, we know, it's a risk. That's why documentation is critical. We start by drawing detailed P&ID, piping and instrumentation diagram for every SIP circuit. And these are the maps that guide operators and engineers. Now, coming to the our nitrogen in SIP technology, as you must be, nitrogen plays a silent but vital role in SIP. Think of it as a guardian angel of the system. In emergency, when oxygen supply fails, nitrogen automatically takes over lance cooling. This prevents overheating the lances and protects the lance also from damage. Now, in a fault condition or shutdown, nitrogen purge starts. It divert stored oxygen safely away from the furnace, preventing overpressure or unwanted entry. It's like a firefighter cleaning the scene. During a startup and shutdown, nitrogen inerting ensure no residual oxygen remains. This prevents ignition risk and stabilize the system. Nitrogen is not just a backup, it's a safety pillar. Now, coming to the oxygen ring main. The oxygen ring main is the lifeline of SIP, designed to deliver up to 15,000 normal meter cube per hour across 24 SIP boxes, and it operates at 20 bar pressure. That's the powerful flow, like a river of energy. The pipe geometry matters. The main ring uses DN150, DN200, that is DN150 to 200 pipes with DN200 preferred for a long run. Branch line to SIP boxes use DN50, DN80, optimized for rapid pulse delivery. Material selection is critical. ASTM 106 grade B is standard, but for the corrosion resistance, TP30 316L stainless may be used near lances. Wall thickness must be handled pressure surges, schedule 40 minimum or schedule 80 preferred. Every joint must be full penetration welded, no galvanizing, no shortcut. And similarly, coming to the uh, nitrogen ring, as we have already discussed, the nitrogen ring mains is designed for agility. It delivers 150 normal meter cube per hour for cooling and up to 1000 normal meter cube hour for the purging. Pressure range from 5 to 20 bar. And as for the pipe sizing is concerned, DN80 to 100 for the main ring and DN25 to 40 for the branches. Now, coming to the coming to those oxygen injection details, as we have shown, this already is being shared. This oxygen ring details also is being shared. And similarly, coming to the nitrogen rings, that already now, coming to the general details, let's talk standard. Every pipe, bend, flange and fitting must be certified for the gas service. Follow local gas codes and oxygen standards. Welding procedure must be certified for oxygen service with root and pass inspection. Cleaning is non-negotiable. Oxygen pipe must be degreased internally to remove hydrocarbon per ISO 14708 or equivalent. This prevents ignition risk. Electrical grounding is mandatory. Lighting protection must be placed and labeling matters. Oxygen pipes are blue, nitrogen pipes are grey, and these are not just color, they are safety signals. So now coming to the our safety table, we can see that snapshot of pipe specification for the oxygen main ring DN200 ASTMA 106 grade B, schedule 80 12.7 mm wall thickness. For branches DN50 schedule 40 5.54 mm. Nitrogen main ring uses DN80 to 100 schedule 40 oblique 80 with wall thickness up to 10.7 mm. Branches are DN25 40 with 3.38 4.5 mm thickness. These numbers are not just specs, they are the backbone of SIP reliability. Every dimension, every grade, every weld contributes to the safety performance deeply.